Today I'd like to talk about an alternative model of black holes proposed by Kawai, Matsuo, and Yokokura, and the follow-up works. So let's start with what's known about black holes, or what people thought about black holes in the conventional model in the old days. So first of all, if you have a classical black hole, you have a Penrose diagram like this. So if you are at distance from the black hole, actually you would never see the horizon until the infinite in time. And you would see everything falling closer and closer to the Schwarzschild radius. And everything that seems to be falling into the black hole would never actually reach the horizon. Now, when you turn on Hawking radiation, you have energy taken away by the Hawking radiation, and the Schwarzschild radius is supposed to shrink over time. So you would naively think that it would make everything even harder to cross the horizon. On the other hand, in the conventional model, the Penrose diagram looks like this. So what people say is actually that now if you are at a distance from the black hole, you would be able to see things falling into the horizon within finite time. So this is a little bit counterintuitive. And so if you ask the person proposing the conventional model, this would be their responses. One of the responses is that the Hawking radiation is extremely weak. For an infalling observer, he can cross the horizon within finite pocket time. And when you turn on a very weak Hawking radiation, it's not supposed to be able to evaporate the whole black hole away within such a short time. So he would still be able to fall into the horizon within finite pocket time. We will see later that this actually, this statement is incorrect, because you can write down explicit solutions to Einstein gravity, which is having a tiny or arbitrarily weak outgoing radiation, but it would prevent infalling observers to cross the horizon within finite pocket time. The second response is that in a conventional model, people assumed that there is actually no outgoing radiation near the horizon. The horizon is a vacuum state. The Hawking radiation only appears at distance. But here in this model proposed by Kawai et al., actually we're assuming that when you see Hawking radiation at distance, you can extrapolate the energy flux back to the surface of the collapsing star. So this is a real difference between the conventional model and the model which I'll call KMY model. In the conventional model, even though you propose that the horizon is a vacuum state in the beginning, actually after the firewall paper, you know that later on it become classical radiation. So here we're just saying that the radiation should be treated like a classical radiation in the beginning and taking care of the back reaction. But let's first look at the KMY model and the issue about whether a tiny radiation could change dramatically the experience of an infalling observer. So in this KMY model, in the beginning they made the following assumptions. For simplicity, we consider a stacked symmetry, and also you consider the collapsing of massless dust. So this is the extreme case of gravitational collapse. Everything's falling toward the center at the speed of light. There's no pressure to prevent things from collapsing. So naively, you would think that this would definitely give you a horizon. However, here, the back reaction of Hawking radiation of massless particles is taken into consideration. Here, I wrote pre-Hawking radiation, meaning that before the collapsing sphere crosses over the horizon, when the surface of the sphere is like extremely close to the horizon, but perhaps a fraction of Planck scale away from the horizon, you would expect Hawking radiation already, because for long wavelength modes, it cannot possibly tell the difference between having the surface inside the horizon, on the horizon, or a fraction of Planck scale away from the horizon. So you expect Hawking radiation. before the horizon appears. And then if you just take into consideration the back reaction of this pre-Hawking radiation, you would see that the geometry is such that the infalling observer would not be able to cross the horizon. So here is the metric to describe the region outside the collapsing sphere. This is the so-called outgoing Vaidia metric. This is the metric people use to describe the outside of a collapsing star with outgoing radiation. It would be equivalent to the Schwarzschild metric if this function A is a constant. A would be the Schwarzschild radius. It's 2 times the boundary mass for the outgoing Vaidia metric. As the star is radiating, the energy is decreasing, and you expect A to be decreasing, and that would give you a positive outgoing energy flux corresponding to the radiation. So the faster the mass decreases, the stronger the outgoing radiation. Now from the metric, you can easily write down the light-like geodesic equations for outgoing and ingoing massless particles. So to check, so if A is a constant, it's Schwarzschild. If A is not a constant but decreasing with arbitrarily weak outgoing radiation, so that A dot can be arbitrarily close to 0 but negative, you will see that the ingoing light-like geodesic equation would never cross the horizon. So that's the statement. You can easily simulate this equation. So here, these pictures are drawn for the case when A follows the trajectory of standard black hole. I mean standard Hawking radiation formula, so that as A is smaller, the radiation is stronger, and then you can plot the trajectory of a massless particle with the trajectory of capital R. You can think of R as the surface of the collapsing sphere, because everything in this sphere is collapsing at the speed of light. Everything in this sphere is composed of massless particles. So the surface of the collapsing sphere, it falls within the background of the outgoing Vaidia metric, and its trajectory would look like this for different initial conditions. You will see that it's always just a little bit outside Schwarzschild radius. If I enlarge this portion, you will see that the Schwarzschild radius quickly goes to 0, leaving the infalling particles at distance. This is actually a generic situation. It's actually easy to understand why the simulation result would be like that. It's just because if you plug in the trajectory of the apparent horizon, R equals A of U, into this expression, ds squared would be negative. Right? For R equals A of U, this is 0. And the second term, because A dot is negative, would be positive. So you have a space-like trajectory, and you know the Schwarzschild radius is shrinking. So what you have is the Schwarzschild radius shrinking at a speed faster than light. That's why nothing can catch up with it. So if you start with a surface which is originally outside Schwarzschild radius, as long as the surface is not shrinking faster than light, it would not be possible for the surface to catch up with the Schwarzschild radius until the Schwarzschild radius goes to 0. After the Schwarzschild radius goes to 0, the universe becomes Minkowski space. And Minkowski space is known to be geodesically complete. And therefore, you can continue these trajectory into the Minkowski space and see that they have no chance of entering the horizon. In Penrose's diagram, what happens is like this. The Schwarzschild solution actually has 2 horizons, the black hole horizon and the white hole horizon for the maximally extended Schwarzschild solution. What we saw was actually that when you decrease the Schwarzschild gradient in the Schwarzschild solution, what you are looking at is actually this part. You are actually looking at the white hole horizon with a shrinking Schwarzschild radius. And that's why you can see from this curve that it's shrinking at a speed faster than light. So when you're focusing your attention on the outside of the collapsing sphere and do analytic continuation with the metric inside the collapsing sphere, you have a Schwarzschild radius, which is not emergent yet. And you would see that this imaginary Schwarzschild radius is shrinking faster than light. That's why the collapsing sphere can never catch up with it. The fact that Schwarzschild solution has two horizons degenerate, you can't really tell the difference by looking at the Schwarzschild coordinates, has to do with the phenomena, the critical phenomena of classical gravitational collapse. So what we're showing is actually just like a classical theory with classical radiation, and it's well known for people doing classical gravity simulations that the collapse is like critical behavior. If you change the parameter infinitesimally, you can switch between having a black hole or having no black hole.
So it's a phase transition?
It's a phase transition, yes. You have critical exponents, etc. Okay, so some people wonder whether you do have Hawking radiation when you say you have no horizon. I was giving you a physical intuitive answer saying that for the long wavelength modes, they cannot tell the difference between having the surface of the collapsing sphere on the horizon or in the horizon or just a Planck scale away from the horizon. People also have done calculations. Essentially, you do a Bogoliubov transformation and you check whether the affine parameter parameterizing light rays would suffer an exponential relation, and you can see that as long as you have something very close to the horizon of the Schwarzschild solution, you do have a Hawking radiation, even when it's a white hole horizon.
What is capital U?
Sorry?
Capital U.
Yeah, so in the calculation, you consider the Minkowski vacuum of the infinite past, and capital U is the light cone time coordinate of the infinite past, and little u is the time coordinate of the infinite future. So what went wrong with the perturbative argument in the conventional model? They say it's a small perturbation by Hawking radiation. But in gravity, when you do general coordinate transformations, quantities change, and small perturbation for one observer is not necessarily a small perturbation for another. So Hawking radiation is weak for a distant observer, not necessarily weak for another infalling observer. And therefore, it makes more sense to say that Hawking radiation doesn't change the viewpoint of a distant observer so much as it does change the viewpoint, the experience of the infalling observer. So for infalling observer, turning on Hawking radiation stops him from falling across the horizon. But for a distant observer, it looks the same. The black hole looks like never really forming. It takes infinite time to see the horizon. Namely, you never see the horizon. Okay, so in the conventional model, what people do is like this. You consider gravitational collapse of matter without Hawking radiation, the classical gravity theory. After that, you get a background metric and you turn on Hawking radiation by studying Bogoliubov transformation with this background metric. And then you say that, okay, in the end, you get Hawking radiation at a distance away from the horizon. Near the horizon, you keep the classical black hole solution. That's how infalling observer can actually fall into the horizon. However, that breaks weak energy condition or energy conservation because you are really receiving Hawking radiation at a distance. So if you are not allowed to extrapolate it back to the surface of the collapsing sphere, you're saying you're either violating weak energy condition by imagining negative energy fluxes flowing into the horizon, or you are saying energy is not conserved. So in that sense, we think it's not consistent. And the consistent approach proposed by Kawani Okura was that you do the following. You consider Einstein equations with an energy momentum tensor that includes both the collapsing matter and outgoing Hawking radiation. And here, by Hawking radiation, we mean including, the pre-Hawking radiation. And technically, the way we do it is the following. You first study the most generic magic for arbitrary energy momentum tensor, including the incoming and outgoing radiation. Without really writing it down, you just write down the most general magic. And then, for this general magic, you compute the Hawking radiation energy flux. And then you demand that it equals this outgoing radiation, and then you solve for G. So it's a consistent approach. You demand that Einstein equation is really satisfied, including Hawking radiation. Although here, again, the difference is that we treat Hawking radiation like the energy flux that's conserved, rather than assuming that it doesn't exist in the horizon. Okay, what do we see out of this? First of all, there is Hawking radiation before the appearance horizon, as I mentioned, and then the back reaction of this pre-Hawking radiation keeps the collapsing surface above the horizon at finite distance. Of course, this possibility was considered long ago in the very early days of studying black holes by Hawking and other people. At that time, they dismissed this possibility because they were afraid of the following. They would imagine that the collapsing sphere would approach to the Schwarzschild radius indefinitely, so that you get an indefinitely large blue shift factor. And if you assume that the radiation really is non-zero near the collapsing surface, you would get a firewall. So at that time, they would avoid this infinite large energy density of Hawking radiation near the collapsing surface by claiming that there is no energy flux near the horizon. But the fact is that if you really take into account of back reaction carefully into your metric, then you would see that even if you have the surface of the flux at the speed of light, you are always at a finite distance away. So this is the equation for light-like beam-folding trajectory. R is the radius of the surface of the collapsing sphere. And here I'm taking the usual formula for Hawking radiation. You could use a different formula. It would only change the expression here. You see that there is a difference between the collapsing surface and the Schwarzschild radius by a finite quantity depending on how fast the Hawking radiation is evaporating. So roughly speaking, the larger the Hawking radiation, you would expect stronger radiation near the collapsing surface. On the other hand, faster Hawking radiation means the Schwarzschild radius shrinking faster, leaving a larger gap between the Schwarzschild radius and the surface of the collapse. And therefore, in fact, you are putting an upper bound on the energy density near the horizon. So let me skip this calculation, but in the end, we get a energy density near the horizon that is inversely proportional to the Schwarzschild radius. So it's still a very weak outgoing radiation. So if you are really standing on top of this collapsing surface, you would still feel like it's vacuum. The energy density is too low, even though we are not ignoring the outgoing radiation. You have a parameter here depending on your reference frame, how fast you are falling toward the collapsing sphere. So, of course, if you have a very weak outgoing radiation, but if you are moving at larger velocity, then you would have a Lorentz transformation factor gamma, right? If you are if you are moving against the radiation at the speed of light, regardless how weak the radiation is, you would always experience an infinite energy density. If you are falling at the speed of light, you still see a large radiation. So in this way, information loss paradox is resolved because everything's only approaching to the Schwarzschild radius at finite distance. You're never really crossing into the horizon. Pre-Hawking radiation takes away your energy before you cross the horizon. And there is always chance of local interaction for the outgoing Hawking radiation to take information away. So the pre-Hawking radiation is created near the collapsing layer, like peeling off an onion. It's written in the paper. So I have only talked about the region, the space outside the collapsing sphere. Now I'd like to talk about the geometry inside the collapsing sphere. The geometry inside the collapsing sphere can be studied in the following way, because we're considering only spherically symmetric configurations. So you can use the theorem, the Birkhoff theorem, and consider infinitely many layers of spherical shells. And between every two layers, you have nothing but outgoing radiation. And every layer is a layer of collapsing dust. And therefore, in the space with only outgoing radiation, you can again use the outgoing Bidia metric, and then you can patch the metric within this layer to the next layer by continuity equation. And then in the end, you can take the limit of infinitely many layers with infinitesimal space in between. What you see in the end is that you get a huge redshift factor, because every layer is approaching to the Schwarzschild radius defined by the total energy enclosed within that layer. And that gives you one redshift factor. With infinitely many layers, you get a humongous redshift factor. So here what we can do is we first write down the metric for arbitrary distributions of energy and arbitrary distribution of velocity of the collapsing sphere. And the energy is allowed to decrease over time, corresponding to heavy radiation taking away the energy. If we demand that the energy is not losing into outgoing radiation, actually we find that the solution is in agreement with the old solution of Tolman metric for collapsing dust. And the metric looks like this. It looks like the outgoing Bidia metric, but with a Schwarzschild radius function depending on R. So you think of many collapsing layers and with different amount of energy enclosed within that layer. And in addition, you have a redshift factor to relate the outgoing Bidia metric in different layers. So this is the result of taking the limit, where this function, the redshift factor psi, given by this function A and B. So given that metric, you can compute Hawking radiation. And if that configuration is sufficiently close to, I mean, if every layer is sufficiently close to its Schwarzschild radius, then you can use the usual formula for Hawking radiation as a good approximation. And that determines the evolution equation for this function A. That tells you how fast each layer is losing energy. Here, capital D is a comoving time derivative. You are imagining following one layer of the collapsing dust. And then the energy going out of the energy flux could be given by the usual formula for Hawking radiation. And then you can check that the energy momentum tensor from the Einstein equation is really composed of infalling dust and infalling dust and outgoing radiation. The outgoing radiation is given by the formula of Hawking radiation. So that's what I mean by asymptotic black holes. What I mean by asymptotic black holes in the title is the following. So in the beginning, you could have different initial conditions. But eventually, assuming that gravitational force dominates over other interactions, every layer would approach to its Schwarzschild radius. So if you wait long enough, you would see a configuration in which every layer is approaching to its own Schwarzschild radius. And also every layer would be accelerated indefinitely by gravitational force until it's moving almost at the speed of light. If you take this limit, then you can actually compute the function A and function psi, and actually you will see that function A would be almost independent of time. This can be understood in the following way. When every layer is approaching to the Schwarzschild radius, there is a huge redshift factor, so that everything is frozen inside the collapsing sphere. So everything would look like not moving, and therefore the density would look like a constant of time. And we have checked, of course, that there is no singularity at the boundary or anywhere. Okay, in case you are wondering about that. And then also the assumption that everything is falling at the speed of light gives you this redshift function. Here, sigma according to Hawking radiation calculation is Planck length squared. So this tells you that you get a huge negative psi for your coordinate r, even when it's a Planck scale away from the collapsing surface. So even if you're looking at a point beneath the collapsing surface that is a fraction of a Planck scale, you get a huge redshift factor, so that everything looks like frozen, and that's why it would appear to you that it's really a black hole horizon, because everything in there would never be able to come out, I mean practically, because it's frozen. It tries to get out at the speed of light, but it's essentially frozen. It looks frozen to you due to this huge redshift factor. And therefore, from the viewpoint of a distant observer, this would be almost indistinguishable from the black hole with horizon. There were other works in the past proposing also that there is no black hole event horizon. Some of them assume that there is still a apparent horizon. Others consider specific models, say scalar field, or the dynamics in the collapsing star. For different reasons, they have made a similar proposal, although here we are trying to say something that's more robust, that's more general. We're only considering semi-classical physics, making the assumption that at large scale, Hawking radiation is also radiation, so you should take into account the contribution of the radiation in Einstein equation. And so this is the conclusion. We got a self-consistent model of black holes with a metric you can use to check things, unlike the conventional model, which I think has no metric. Semi-classical large-scale physics only. We didn't use any UV physics or string theory. There's no firewall unless you are moving towards it at the speed of light or close to the speed of light. There's no horizon unless you propose it's already there in the beginning. But then that doesn't make information loss. You could have information inside the horizon in the beginning, but it's never your information. So there's no new information losing by seeing anything falling into the horizon. And we propose that in observations, when you see something that looks like a black hole very much, it's actually an asymptotic black hole without horizon. So most important comment I'd like to make is that we have the explicit metric. We can verify all the statements by additive calculations rather than hand-waving arguments saying you can ignore this or ignore that. Thank you.
Are there questions? Comments?
So back in the early 90s, there was this large activity in models of black hole evaporation where you compute the back reaction and solve for the black hole, I mean the CGHS model, all that sort of stuff. Models. There are lots of papers where you compute the excitation by the stress tensor and then solve consistently for the dynamics. So that all that literature resulted in black holes behave, paradoxically. There's information loss.
You're talking about the 2D?
The 2D stuff,
Yeah.
or there's a dimensional reduction. It would be like the S-wave approximation, but the point was, it was supposed to be a self-consistent model where you took into account the back reaction and then put that back in Einstein's equation, solved it self-consistently, but the conclusions you quite different from what you were saying.
Actually, in the 2D case, people did see that in some cases, you never see the horizon. So I should say more clearly that here I'm making the assumption that the black hole evaporates according to the usual Hawking formula. If you are changing the formula of radiation, then you could get a horizon in the end. What we see is just that the metric in the end had, the metric is geodesically incomplete. In those cases, you know you have a horizon. In the 2D case, what people found was that actually, if your initial state is of very low energy density configuration, then also they say that you don't see the horizon. So the difference is what's the critical energy density. There's a this is like critical phenomena. You can tune your equation for Hawking radiation so that you have horizon or no horizon. And also you can tune your initial energy density to have horizon or no horizon. So what I'm really saying is that even if you do have a horizon, this is what I didn't say, but maybe I should emphasize it. If you do get a horizon by tuning your initial configuration density or Hawking radiation formula, it would be like a classical horizon. So still you have no information loss. So this is consistent with the 2D theory, although we're hoping that the critical density is different.
I mean, yeah, just guess. I mean, that people at that time concluded that approach still led to information loss.
Yeah, but their formulas are not the same because the anomaly equation and so on in 2D is different from 4D.
Do you think you can distinguish your model from the conventional black hole by considering the large retardation? For example, if you consider two black hole mergers, your model may give a different prediction for the gravitational wave radiation.
Well, yeah, that depends on how well you do the simulation. I think when people consider the merging of two black holes, they are ignoring Hawking radiation, right? So they are only looking at the classical solution. And you saw that for classical black hole, actually for a distant observer, you would never see a horizon. So.
It's in your model, maybe the inside of the black hole structure would give some effect.
The inside that depends on the redshift factor. So I did some check in numbers. The time it takes for something that's like 1 Planck scale beneath the surface of collapse for something of the mass of a sun, the time it takes to get out is like 10 to some power of the age of the universe. So the redshift factor is tremendously huge. So for all practical purposes, for everything that can happen to be observed within your lifetime, you can't tell the difference.
Even for non-spherical.
Oh no, everything I say is about spherical. Smash.
The last question.
As you mentioned in the middle of the loss of unitarity is a consequence of black hole. But in the conventional model, in your model, unitarity is okay or it is still lost?
It is okay. I mean, everything happens locally, so there's no obvious reason why you would lose unitarity as long as you can still use low energy factor theory.
So then can you point out how the difference of concerning unitarity, how the unitarity is lost in the conventional model and unitarity is okay for it?
In conventional model, everything falls into the horizon, but you have Hawking radiation appearing outside the horizon. So you need non-local interactions to transmit information.
Okay, so let's thank Pei-Ming again.